So the very last section we're going to cover in this unit is techniques for graphing. Now that we've got these basic functions, we're going to apply a bunch of different shifts, transformations, reflections, things like that, that will alter that graph but still keep that same basic shape. So let's start with our horizontal and vertical shifts. So we're going to assume C is a positive number, and what we're going to do in each of these instances is add C, subtract C on the outside, add C, subtract C on the inside. Each of these will do something similar. We're going to shift the original graph by C units. Where that C is located, and based on it being plus or minus, indicates which direction you shifted in. So if you look at the first two instances, those are on the outside. So you've input X, you find the Y value. Now I'm adding or subtracting a new constant. So this is going to move it up or down. In the case you add something positive, it does what you want, it moves it up. In the case you subtract, it's going to move that graph down. In these second two instances, you're altering the X. So I'm changing the X value. This is going to move it horizontally, so either left or right. The kind of key that I like to remember is that when you alter the X, it does the opposite of what you actually want. So you've got X plus C. You would think that would move the graph to the right, but it's going to do the opposite. It moves it to the left. When you subtract C, you're thinking, oh, negative, that's the left. But no, this is going to move it to the right. So the X behaves opposite of what you would normally like, where the Y does exactly what you think it would do. So let's go ahead and just consider the graph of Y equals X squared. And I'm going to apply these transformations dealing with C equaling 4. So if I have Y equals X squared plus 4, that's going to take our graph of Y equals X squared and shift it up 4 units. So let's go ahead and just ghost in our Y equals X squared. Goes through 0, 0, 1, 1. If you plug in 2 or negative 2, you get 4. So here is our graph of Y equals X squared. Now when I add 4 to the outside, it's going to shift every single point up by 4. So 0 gets shifted up to 4. The 1, 1 gets shifted up to 1, 5. Negative 1, 5. And then you keep that same basic shape. So it still keeps the parabola shape. So here's Y equals X squared plus 4. In the next one, if I subtract 4, the only difference is that's going to move that down. So my original graph that I'm going to sketch in, or my mother parabola, which is right here, I'm going to dot in. Now I'm going to subtract 4, so each point is going to get moved down 4. So we go 0, negative 4, 1, negative 3, negative 3. If you plug in 2, it was originally at 2, 4, so it gets moved down 4 to 0 and 0. And then our graph looks like this. Okay. And you don't need to be an expert grapher, just do your best, but know what each of these means. Now, if we have Y equals X plus 4, that's going to be the opposite. So you would think positive 4, but no, it's going to do the opposite. And let's think of why that is. So let's plot in our few points that we are comfortable with. So here is Y equals X squared. Now, if you plug in X equals negative 4, you'd have negative 4 plus 4 squared. That's going to give you 0 squared. So that's why it ends up moving it to the left 4. Likewise, this point gets moved 1, 2, 3, 4 to right here. To right here. Same thing, if you move 1, 1 to the left 4, it will go through right here. And then we'll keep the same basic shape. So this Y equals X plus 4 squared. And now if I have Y equals X minus 4, that's going to shift our base graph to the right. So here is our base parabola. And now that point at 0, 0 is going to get moved to 4, 0. And then it keeps the same basic shape. Okay. So let's go ahead and kind of combine these two. Let's graph h of x equals the absolute value of x plus 2 minus 1. So let's pick out our two transformations. We've got this plus 2 in here. So that's attached to the x, that's going to move it left or right. And since it's positive, that moves us to the left 2. The minus 1 on the outside affects the y, and it behaves what it wants. It shifts it down 1. So I'm going to ghost in our absolute value function, and then I'm going to apply these two transformations. So the absolute value of x is our v-shaped function. Looks just like this. Now I'm going to go ahead and I'm going to shift it left 2. So it was at 0, 0, gets moved to 2, 0. And then I keep the same shape to the best of my abilities. And so this is just y equals the absolute value of x plus 2. And now I want to shift it down 1. So this point at negative 2, 0 gets moved down to negative 2, 1. And we go ahead and draw our absolute value function in. So this is y equals the absolute value of x plus 2 minus 1. Okay. Now the next type of transformation we're going to deal with is reflections. So in this case, it still keeps the same type of behavior. You've got negative f of x. It's on the outside, so that's going to deal with the y. So it deals with the y values, which means it's going to reflect it about the x-axis. So it's going to flip down, make all of our y values negative. When it's attached to the x, when x is positive, it becomes negative. That's going to flip it over the y-axis. So let's just consider the graph of y equals the square root of x. Remember, the square root is going to give you positive numbers, but throwing this minus sign out front is going to make them all negative. So it's going to take this basic graph and flip it about the x-axis to give us this. If I put that negative sign on the inside, then it's going to flip that graph about the y-axis. So think you can only input negative values for x now to make sure you get something positive underneath the radical. So it flips it across the y-axis. So in combination, we do have a specific order we need to apply these transformations in. First thing you want to do is do any horizontal shifts. Then you're going to apply the reflections and then do your vertical shifts last. So make sure you follow this specific order. If you don't, you're going to have to be very, very, very careful about how you do the reflections and how you do the shifts. So let's look at an example. We've got f of x equals 3, the square root of 3 minus x plus 2. So I've got three things going on. First, I've got the negative x. That's going to be a reflection. The plus 2 tells me I'm going to move it in the vertical direction. And then the positive 3 tells me I'm going to apply to the horizontal. So my first is a vertical or is a horizontal shift that I have to go through. And that's a positive 3. So it corresponds to shifting our graph left 3 units. So if we think of this, that's y equals the square root of x plus 3. Then I'm going to go ahead and apply this reflection, which is the negative x. That tells me I'm going to reflect about the y-axis. So you're replacing x by negative x to give us this square root of 3 minus x. Then finally, we shift it up 2. And so we get our final function. So I want to apply all of these in one piece. So first thing I want to do is I want to take our graph of the square root of x and I want to shift it up 3, or left 3. So we go ahead and take this point that's at 0, 0, and we're going to move it to the left 3 to negative 3, 0. So here is our first transformation. Now I'm going to go ahead and do that reflection about the y-axis with this graph in green. So I've got the graph in green. My second step is I want to go through and I want to reflect it. So I'm going to flip it completely to give us that second transformation. And then finally, I've got to do that horizontal shift. So this is our third step. I want to go and move it up too. So I'm going to take our graph and move it up too. So you can draw everything on the same graph if you want. If you need to take it piece by piece, feel free to do that. Get practice with whatever you're comfortable with. Now, the last transformation we're going to learn about is about stretching and compressing. This one's a little bit harder and it's not as important because really we have vertical and we have horizontal stretches and compressions, but these ones that are attached to the X really can just end up corresponding to a vertical transformation as well. So don't spend as much time stressing out about these. Focus more on the first types, the reflections, and then the horizontal and vertical shifts. But we're going to let C be a number that's bigger than 1. Based on what you multiply your y value or x value by, it's going to tell you to stretch or compress your graph. We're multiplying by this factor on the outside, so that's going to deal with a vertical stretch or compression. So both of these are vertically. If you think of multiplying by 3x, that's going to make those y values bigger. It's going to stretch it in the y direction. If you're dividing by something, it's going to compress it. Okay. In the case that you are multiplying by the factor of c on the inside, those deal with horizontal stretches and compressions, and it's the reverse. So you multiply by a large number, it's going to compress the graph. If you divide by something, it's going to give you a stretch instead. So let's just look at some examples of these, but again, don't spend too much focusing on it. If we have the graph of y equals x squared, and I go ahead and multiply by 2 on the outside, if you input, we're going to deal with the same 0.11 every time. If I input x equals 1, my y value is going to be 2 instead. So it's going to stretch this up in this direction of the y-axis. If I multiply by a half, when I input x equals 1, my output will be a half instead. So it's like I've gone and I've put a brick on top of the function and I've pushed it down and compressed it vertically. Now if we put the factor of c on the inside of the function, so y equals 2x squared. Really, the reason these ones aren't as important is because here, you just distribute out that square, it's 4x squared. It's going to be a vertical thing as well. So these ones aren't as essential to know. So if we go ahead and graph this, if you plug in x equals 1, the output will be 2 squared. So when you input 1, your output's going to be 4 still. So you've now, in the x direction, squished it in. So here, we've gone ahead and stretched it up. Now we've pushed it down. And here, we've pushed it inside. If you have 1/2 x to the second power, when you input x equals 1, it's a half squared or 1/4. So you've gone ahead and you've stretched it in the x direction. So it's like we've taken this graph and pushed it out. But see, these graphs honestly look very similar to each other, which is why there's not super significant difference between them. Okay? So spend more of your time focusing on those first couple techniques. But now that we do have this, we do have a specific order to apply the transformations in as well. You want to still do your horizontal shifts first, but now you're going to apply stretches and compressions here, then your reflections, and then your vertical shifts. So make sure you know these basic graphs down pat, and then you'll be able to graph a whole bunch more based on it. Okay? So now with this, we've got a bunch of different symmetry that can pop out. So for x-axis symmetry, if you look across the x-axis, you have the same function up top, same function on the bottom. So it's symmetric across the x-axis. So really, this point here, AB, corresponds to the same point A, negative B. For y-axis symmetry, if you look on either side of the y-axis, you have exactly the same graph. So when you have the point AB, you're also going to have the point negative AB, so kind of like a parabola. For origin symmetry, if you have the point AB, then negative A, negative B will on your graph. It's really like you've gone ahead, reflected it across the y-axis, and then reflected about the x-axis. So it's kind of like you have a rotation in here. So the way to actually test for symmetry, not just by looking at it graphically, is going to be by doing one of three things. So to test for x-axis symmetry, if you look at the value of x, when it's the same x value, you have opposite y values. So you're going to replace y with negative y and see if you get exactly the same thing back. You should. For y-axis symmetry, if you replace a by negative a, you should still get the same y output. So you should get an equivalent expression. So you replace x with negative x and check for the same thing. For origin, you have to replace both of these by the negative values and check to see if you get the same thing. So replace x with negative x and y with negative y to check for an equivalent equation. So let's test and determine what types of symmetry the equation or graph has. So once you go through, and if you do find one, still keep testing. Test every single type. So let's start with x-axis symmetry. Then we'll do y-axis, then we'll do origin. You want to test all of them. So for x-axis, I replace the y value with negative y, and I want to see, does it change the equation? Well, no, I can't rearrange this and get exactly the same thing. So there's no x-axis symmetry. For y-axis, I replace x by negative x, so we get negative x squared. But that minus sign really just gets destroyed, and I end up with exactly the same thing. So this one does have y-axis symmetry. Now for origin, I'm going to replace x by negative x, y by negative y, and I'm going to see, do I get the same thing? No, because this will disappear, but I can't get this minus y here to disappear, so I won't get the same expression. If we look at this next one, same thing. We're going to test for x-axis, y-axis, and then origin. So for x, I replace y by negative y, but I'm going to take negative y and square it, so really it disappeared. So we do have x-axis symmetry. For y-axis, replace x by negative x, but when you square a negative number, it's going to destroy that minus sign, so we also do have y-axis symmetry. And for origin, I replace both of them, and since I'm squaring both of these negatives, you get the exact same thing back, so we have origin symmetry as well. So this is why once you find one, you still have to test the others. Don't forget about those. Now if we look at this next graph, if we look at this top piece, if you flip it down, you get exactly the same thing here. So this one has x-axis symmetry. If I look at this, I definitely don't have x-axis symmetry because here's 1/2. If I flip that over, I would really have this piece, so no x-axis symmetry. If you had y-axis symmetry, if you took this piece and flipped it over, you'd really form a diamond, so no y. And likewise, no origin. So this just has no symmetry. Okay? So with this, it leads to two special properties, which are even and odd functions. So if you take your function and evaluate it at negative x and you get the same thing back, kind of like the parabola, it would destroy that minus sign. And you can do that for every single value of x in the domain. Then you can say this is an even function. If you take your function, evaluate it at negative x, and the minus sign spits out for all values of x in the domain, then it's going to be an odd. So for even, the minus sign disappears. For odd, the minus sign spits out. So let's go ahead and determine algebraically if the function is even, odd, or neither. So what we're going to do is just evaluate this function at negative x. So I'm going to take 7, times it by negative x to the 4th, add negative x squared. Since both of those are even powers, those minus signs disappear, and you end up with exactly the same function in return. So this one is an even function. If I look at this next one, I go ahead and take g and evaluate it at negative x. So I get 7 times negative x to the 3rd minus 4 times negative x. Since this first one is an odd power, the minus sign pops out. Negative 4 times negative x is 4x. Well, if I factor a minus sign out, I get the same expression back right here. So it's really negative times my original function. So it's an odd function. So another property that really kind of pops out, if a function's even, then its graph is going to be symmetric with respect to the y-axis. And if a function is odd, its graph is symmetric with respect to the origin. You cannot have a function that has x-axis symmetry because that would fail the vertical line test. So it's only going to have y-axis or origin symmetry.